The centre of the galaxy is 19 years away. Not 19,000. 19. 26,000 light years, crossed inside a single working career by a crew who arrive healthy and in their 40s. That is not speculation. It is settled arithmetic, and every piece of it has been measured. Atomic clocks flown around the world on scheduled airline flights came home disagreeing by exactly the predicted number of nanoseconds. Particles that should die 600 metres up arrive at sea level in their billions. The satellites overhead correct for 38 microseconds a day, and if they stopped, you would be lost by tomorrow. So the trip is real. The ship gets there. The crew survives. And tonight you are going to find out what it would actually take to come back from Sagittarius A star. Because the answer is not fuel, and it is not shielding, and by the end you will know exactly what it is. Get cozy. If you are the kind of person who enjoys watching a solved problem turn out to have an unsolvable one hiding behind it, a slow like and subscribe helps this channel find more minds like yours, because by the end of tonight, the word return will not mean what it meant when you sat down. Now, let's slowly settle in. There is a place in this galaxy that has a fixed address, and almost nobody thinks of it that way. We're used to thinking of space as a direction rather than a set of destinations. Up, out, away. The night sky reads as a surface rather than a map, and the things scattered across it feel less like places you could travel to, and more like decorations on the inside of a dome. But there is one object out there that astronomers can point to with a precision that would satisfy a surveyor. They know where it is. They know how heavy it is to within a fraction of a percent. They have watched things orbit it for more than 3 decades, and they have taken its picture. It sits at the exact centre of everything we belong to, and every star you have ever seen, including the sun, is falling around it right now. Its name is Sagittarius A star, and tonight we're going to go there and come back. That last part is the whole reason we are here. Going is not the hard part. That will surprise you, and it should, because everything you have ever been told about space travel has been framed around the difficulty of getting somewhere. Tonight the difficulty is going to sit somewhere else entirely, in a place you will not see coming, and by the end you will know exactly what it would actually take to come back from Sagittarius A star. I am going to withhold that answer until the very end, and I want to be honest with you about that now, because the shape of the answer only makes sense once you have carried the weight of everything before it. So let us begin with the destination, because it is real, and it is measured, and it deserves to be introduced properly. On the 13th and 14th of February, 1974, 2 radio astronomers named Bruce Ballack and Robert Brown pointed the Greenbank interferometer at the constellation Sagittarius. They were looking toward the centre of the Milky Way, which is a difficult thing to do, because the centre of our galaxy is hidden behind an enormous quantity of dust. In visible light, that dust dims the galactic centre by something like 30 magnitudes. That is a factor of about 1 trillion. You could build a telescope the size of a city, and you would still see nothing at all, because the light simply does not get through. Radio waves do get through, and when Ballack and Brown looked, they found something that should not have been there. A compact, unresolved, unusually bright point of radio emission sitting at the precise dynamical centre of the galaxy. Not spread out, not fuzzy, a point. Robert Brown gave it its name 8 years later, in 1982. He borrowed a convention from atomic physics, where a small star symbol is used to mark an atom in an excited state. He said the source was exciting. So the object at the heart of the Milky Way is called Sagittarius A star, and the star in its name is a piece of notation, not a piece of astronomy. There is a small pleasure in that, I think. The most important object in our galaxy is named after a punctuation mark. For the next 30 years, the case that this thing was a black hole was built without a single picture of it. It was built out of orbits. 2 teams did the work, independently and in competition. One was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. The other was led by Andrea Ghez at the University of California, Los Angeles. Both groups did the same audacious thing. They picked out individual stars near the galactic centre, and they tracked them, year after year, for more than 1/4 of a century. They used adaptive optics, which is a technology that reshapes a telescope mirror hundreds of times a second to cancel out the blurring of Earth's atmosphere. Without it, the galactic centre is an undifferentiated smear. With it, you can resolve individual stars, and once you can resolve them, you can watch them move. What they saw was a group of stars, now called the S stars, moving on closed elliptical orbits around a common focus. Ordinary Keplerian ellipses, the same shape that Mars traces around the Sun, except these orbits were tiny and fast and centered on something that emitted almost no light at all. If you can watch a thing orbit, you can weigh what it orbits. That is the oldest trick in celestial mechanics, and it does not care whether you can see the central object. Genzel's team and Gez's team fed decades of positions into the same equations Kepler and Newton would have recognized, and the answer came back the same from both directions. The thing at the center of our galaxy weighs 4.297 million times as much as the Sun, and the modern uncertainty on that figure is about 0.3%. In 2020, Genzel and Gez shared half of the Nobel Prize in Physics for that work. Now hold that mass in your head for a moment and let me give it a size, because the size is the part that surprises people. The radius of a black hole's event horizon depends only on its mass, and the conversion is simple, about 2.95 kilometers for every solar mass. 4.3 million solar masses works out to an event horizon radius of roughly 12.7 million kilometers. The horizon is therefore about 25.4 million kilometers across. That sounds enormous, and it is, but let me put it against something familiar. The radius of the Sun is about 696,000 kilometers, so the event horizon of Sagittarius A star is about 18 times the radius of the Sun, and Mercury orbits the Sun at an average distance of about 57.9 million kilometers, which means that if you took the entire event horizon of the supermassive black hole at the center of our galaxy, the thing that 400 billion stars are wheeling around, and you set it down where the Sun is, it would fit comfortably inside the orbit of Mercury. 4 million suns, folded into a space smaller than the innermost planet's orbit. That is not a metaphor. That is the measurement. And then, on the 12th of May, 2022, the Event Horizon Telescope collaboration released the picture. They had linked 8 observatories on 4 continents into a single virtual telescope effectively the size of Earth, with an angular resolution of about 20 microarc seconds. To give you a sense of what that means, it is roughly the sharpness you would need to read a newspaper lying on a table in New York while sitting in a cafe in Paris. What came out was a ring of emission with a dark center. The shadow of the horizon at exactly the size general relativity predicted for that mass at that distance, with no fudging and no free parameters. There is one more thing you should know about it before we go, and it is the least intuitive fact in this entire opening. Sagittarius A star is starving. We tend to imagine supermassive black holes as furnaces, and some of them are. Quasars are the brightest sustained objects in the universe, precisely because they are black holes being fed enormous quantities of matter, which heats up and screams as it falls. Sagittarius A star does almost none of that. Its total light output is somewhere between 100 millionth and a billionth of the theoretical maximum for an object its size. It captures gas from the winds of nearby stars and then blows almost all of it back out again before it ever reaches the horizon. Only a trickle actually falls in. That matters more than it sounds. If Sagittarius A star were feeding the way quasars feed, it would outshine the rest of the Milky Way combined, and the radiation reaching Earth from 26,000 light-years away would have sterilized this planet long before anything crawled out of the ocean. We do not merely live in a galaxy with a supermassive black hole at its center. We live in a galaxy with a quiet one. The stillness of that object is one of the conditions of our existence, and nobody put it there on purpose. There is a second reason the quiet is surprising, which is that the neighborhood is anything but empty. Wrapped around Sagittarius, a star is something called the nuclear star cluster, one of the densest collections of stars anywhere in the known universe. Tens of millions of stars are packed into a few parsecs of space, at densities millions of times higher than the comfortable, spacious neighborhood the Sun occupies out here in the suburbs. If Earth orbited a star in that cluster, the night sky would hold thousands of objects brighter than Venus, and there would be no such thing as true darkness. All of that material is available. All of it is being stirred by the gravity of 4 million suns, and still, almost none of it falls in. In 2014, astronomers thought they were finally going to watch it eat. A cloud of gas known as G2 was on a trajectory that would take it close to the black hole, and the predictions were dramatic. Fireworks, a feeding event, something we could watch happen live. What actually happened was very nearly nothing. G2 passed by, got stretched a little and carried on. The current thinking is that it was never really a naked gas cloud at all, but a dust-shrouded star holding itself together with its own gravity. The galaxy's centre had one chance to put on a show in our lifetime, and it declined. So that is the address. 4.3 million solar masses, a horizon 25 million kilometres across, silent, dark, quiet, and utterly permanent on any timescale a human being can imagine. It was there before the first cell divided on Earth, and it will be there long after the sun has burned out. Write it down, because I want you to notice something later about which of tonight's two addresses is the one that lasts. There is only one number left to give you, and it is the number the entire rest of this video is going to be built on, the distance from here to there, 8.28 kiloparsecs, 26,000 light years, give or take 1,000. That is the gap, and now we need a ship. I am going to do something now that I do not usually do, which is give you a spacecraft for free. Ordinarily, this is where a video like tonight's would spend 40 minutes explaining why you cannot have one. It would walk you through the rocket equation and mass ratios with more zeros in them than there are atoms in your body, and the fact that chemical propulsion is so hopelessly inadequate for interstellar distances that the numbers stop being physics and start being comedy. All of that is true. None of it is what tonight is about. So I am going to acknowledge it in 3 sentences and then set it down on purpose. Here are the 3 sentences. Building a ship that can do what we are about to do would require converting a quantity of matter thousands of times the mass of the ship itself directly into kinetic energy. Twice, with essentially perfect efficiency. Nothing humanity has built or seriously designed comes within many orders of magnitude of that. It is, as far as anyone can currently tell, beyond us. It is worth knowing exactly how far beyond us, because the gap is not a small one, and I do not want to pretend otherwise. The fastest object human beings have ever built is the Parker Solar Probe, which reached something close to 692,000 kilometers per hour as it whipped past the Sun. That is a genuinely enormous speed. It is also about 0.06% of the speed of light, and at that speed, Sagittarius A star is roughly 40 million years away. Voyager 1, which is the fastest thing we have ever sent outward rather than inward, is travelling at about 17 kilometers per second. At that pace, the trip we are about to take would last 459 million years. The dinosaurs would have appeared and vanished twice over before the spacecraft arrived. Fine. Have it anyway. The reason I'm handing it over rather than arguing about it is that the interesting problem in this journey is not the engine. I promise you that. The interesting problem is hiding behind the engine, and as long as we are staring at the fuel gauge, we will never see it. So take the ship. It is yours. Let us find out what it actually costs to use. The ship works like this. It accelerates at a constant 1g. That is not a performance figure. It is a comfort figure. 1g is the acceleration you are experiencing right now, sitting or lying wherever you are, held down by the mass of the Earth. If a spacecraft accelerates at exactly that rate, everybody inside it has normal weight for the entire voyage. There is no floating, no fluid shifting up into your face, no bone loss, no muscle wasting, none of the slow physiological unravelling that makes real long-duration spaceflight such a grim business. You could set a glass of water on a table aboard this ship and it would sit there, perfectly still, for 19 years. The flight plan is equally simple. The ship accelerates for the first half of the distance, then turns around and decelerates for the second half, arriving at the destination at rest. There is no coasting phase, there is no cruise. From the moment the engines light until the moment they shut down at the far end, the ship never stops accelerating. Remember that phrase. I am going to come back to it later, and it is going to mean something rather different when I do. What is strange about this ship, and I want you to notice it now because it matters at the halfway point, is that absolutely nothing about the journey feels fast. Inside the hull there is no sensation of speed at all. There is no shudder, no rising whine, no pressure in the chest. A dropped cup falls at 9.81 meters per second squared on the first day and on the last. Coffee pours straight down. If you woke up aboard with no windows and no instruments, you would have no way of telling whether you were in flight or parked in a hangar on Earth. There is a small curiosity buried in this too. Under a constant 1g, simple Newtonian arithmetic says the ship would pass the speed of light after about 354 days. It does not, of course. Instead, the velocity creeps closer and closer to light speed and never touches it, while a different quantity, the one that actually matters tonight, climbs without any limit at all. So what does that buy? The mathematics of this is called the relativistic rocket problem, and it has been worked out in complete detail for decades. The key constant is the speed of a light divided by 1g, which comes out to 0.969 years. That number is the heartbeat of the whole calculation, and when you feed 26,000 light years into it, you get two numbers out. The first number is 19.8 years. That is the time that passes aboard the ship on the outbound leg. 19 years and about 10 months. A crew that launches in their late 20s arrives at the supermassive black hole at the centre of the Milky Way in their late 40s. They arrive in good health, at normal weight, having aged exactly 19 years and 10 months, having crossed 26,000 light years of the galaxy. Sit with that for a second, because it is genuinely one of the more generous facts in physics. The centre of the galaxy is not out of reach. It is not a multi-generational problem. It is not something you hand to your descendants. 26,000 light years and a career. One person, one working life, and you are there. I want you to hold on to that phrasing too. 26,000 light years and a career. It is going to come back at the end of tonight, and when it does, it will turn out to have been a quotation for something else entirely. Now here is the second number. 26,004 years. That is how much time passes on Earth while the ship makes that same crossing. Both numbers are correct. Both describe the same journey. Nobody's mistaken. Nobody's using the wrong frame. Nobody has made an arithmetic error. The crew genuinely experiences 19 years and 10 months. The Earth genuinely experiences 26,004. The universe simply does not agree with itself about how long the trip took, and there is no higher court to appeal to. That gap is what tonight is about. Everything else is detail. Before we go any further, let me show you something about the shape of this that will make the rest of the video make sense. Because your intuition about distance is about to fail you, and it is worth watching it fail in a controlled way first. Take the same ship, the same 1G, the same accelerate then decelerate profile, and point it at a series of different destinations. Here is what the crew pays, in years of their own lives, one way. Proxima Centauri, the nearest star 4.25 light years away, costs 3.5 years. Sirius, at 8.5 light years, costs 4.6 years. The TRAPPIST-1 system, 40 light years out, with its 7 rocky planets, costs 7.3 years. Betelgeuse, roughly 550 light years away, costs 12.3 years. The Crab Nebula, 6,500 light years away, the wreckage of a star that Chinese astronomers watched explode in the year 1054, costs 17 years. Sagittarius A star, 26,000 light years, costs 19.8 years. The Large Magellanic Cloud, a whole satellite galaxy, 163,000 light years away, costs 23.3 years. The Andromeda Galaxy, 2.5 million light years away, costs 28.6 years. And the Virgo Cluster, 54 million light years away, 1,000 galaxies bound together in one of the larger structures in this part of the universe, costs 34.5 years. Look at what just happened in that list. The distances span a factor of about 13 million from top to bottom. The costs span a factor of 10. Going 100 times further does not cost 100 times more. It costs another 9 years. Andromeda, 2.5 million light years away, an entire separate galaxy containing 1 trillion stars, is a 29-year commitment. That is less than a mortgage. It is roughly the working life of a nurse. This is the compression, and it is the single most important thing to understand about relativistic travel. Once you're moving fast enough, distance essentially stops being a cost to the traveller. The universe becomes flat and near and cheap. Everything is a few decades away. Everything. But look again at that list and ask a different question. Ask what those same journeys cost the people who stayed behind. For Proxima, it is about 6 years. For Betelgeuse, 5.5 centuries. For Sagittarius A star, 26,000 years. For Andromeda, 2.5 million. The traveller's ledger compresses. The home ledger does not. It never compresses at all. It just runs at exactly the rate the distance demands, 1 year per light year, forever. 2 ledgers, same trip, and only one of them has a bargain in it. So we have our ship, we have our destination, and we have the 2 numbers that will not reconcile. What we do not yet have is any sense of why. Why should moving fast do this? Why should the universe permit a crew to cross the galaxy in a working career, while the galaxy takes 26,000 years to watch them do it? That is not a philosophical question. It has a specific, measured, thoroughly confirmed answer, and it has been sitting in the pocket of nearly every person listening to this for years. Let us go and look at what speed actually does to a clock. The phone in your pocket is currently correcting for the fact that time runs at different speeds in different places, and it is doing it about once a second, and if it stopped doing it, you would be lost by tomorrow morning. I want to start there, because time dilation has a reputation problem. It sounds like the kind of idea that lives in thought experiments and film scripts, something you're asked to accept on the authority of a man with wild hair who died in 1955. It is not that. It is a measured quantity. It is engineering. It is in the specification documents of hardware you rely on, and it has been directly observed in laboratories, in the upper atmosphere, aboard commercial airliners, and in the difference between two brothers. Here is the mechanism, as simply as I can put it. When something moves relative to you, its clock runs slow relative to yours. The factor by which it runs slow is called the Lorentz factor, written as the Greek letter gamma, and it is 1 divided by the square root of 1 minus the velocity squared over the speed of light squared. You do not need to hold that formula. You need to hold its shape, because the shape is the whole story. The shape is a cliff. At 1/10 of the speed of light, which is 30,000 kilometers per second, which is roughly 3,000 times faster than any spacecraft we have ever launched, gamma is 1.005. That is a time dilation of half of 1%. 10 years of travel would buy you about 18 days. It is nothing. At half the speed of light, gamma is 1.155. Still small. At 90% of light speed, gamma is 2.29. Now your clock runs at less than half the rate of the clocks you left behind. At 99%, gamma is 7.09. At 99.9%, gamma is 22.4. At 99.99%, gamma is 70.7. Do you see it? The curve is almost perfectly flat across the entire range of speeds that any real object has ever travelled, and then it turns and goes vertical. All of the effect is crammed into the last sliver of approach to light speed. This is why time dilation feels like fiction to us. We live our entire lives and run our entire technological civilization in the flat part of the curve. Everything we have ever done is happening in the first pixel of that graph, but the flat part is not zero. And because it is not zero, we have been able to measure it. In October of 1971, two men named Joseph Hafele and Richard Keating did one of the most charmingly literal experiments in the history of physics. They took 4 cesium beam atomic clocks, bought them seats on scheduled commercial airline flights, and flew them around the world, once heading east, with the rotation of the Earth, once heading west, against it. Then they brought them home and compared them with identical clocks that had stayed at the United States Naval Observatory. Relativity made a specific prediction for each direction, combining the effect of the aircraft's speed with the effect of its altitude in Earth's gravitational field. Eastward, the prediction was that the flying clocks would lose 40 nanoseconds, with an uncertainty of 23. The measurement came back at 59 nanoseconds lost, with an uncertainty of 10. Westward, the prediction was a gain of 275 nanoseconds, with an uncertainty of 21. The measurement came back at 273, with an uncertainty of 7. 275 predicted, 273 found, on a commercial airliner, with clocks that had their own boarding passes. There is an older and stranger confirmation happening over your head right now. When a cosmic ray strikes the upper atmosphere, roughly 15 kilometers above you, it produces a shower of particles, and among them are muons. A muon is essentially a heavy electron, and it is unstable. Left alone, a muon lives an average of 2.196 microseconds before it decays. That is its lifetime, measured in laboratories thousands of times, and it is not negotiable. Now do the arithmetic. Even travelling at the absolute maximum possible speed, the speed of light itself, a particle that lives 2.2 microseconds can cover about 660 meters. 660 meters out of 15,000. By any reasonable accounting, essentially no muons should ever reach the ground. The number that should arrive at sea level is close enough to zero that you would never build a detector for it. They arrive in enormous numbers. Several are passing through your body every second as you listen to this. They arrive because they are moving fast enough that their internal clocks are running slow, with Lorentz factors typically in the tens, and the 2.2 microseconds they experience corresponds to far longer down here. The muons are not doing anything clever. They are simply living their ordinary, brief, fixed lives, and the atmosphere is going past them contracted to a fraction of its thickness. If you want it done in a laboratory instead of the sky, physics has that too. In 1977, a team at CERN led by John Bailey published a result in the journal Nature. They had circulated muons in a storage ring at a Lorentz factor of 29.33 and measured how long they lived. The rest lifetime is 2.198 microseconds. The measured lifetime in the ring was 64.42 microseconds. That is a dilation confirmed to about 1 part in 1,000. That same experiment answered a question people often ask at this point, which is whether it is the acceleration doing the work rather than the speed. The muons in that ring were being whipped around a curve at accelerations of something like 10 to the 18g. If acceleration affected the decay rate, it would have shown up there, monstrously. It did not. Acceleration does nothing to a clock. Speed does everything. None of this was new even in 1977. The first laboratory confirmation of time dilation came in 1938, when Herbert Ives and Gordon Stillwell measured the transverse Doppler shift in fast-moving hydrogen ions, and found exactly the shift relativity demanded. In 1941, Bruno Rossi and David Hall counted muons at the summit of Mount Washington, and then again at sea level, and found far more surviving the trip than any non-relativistic accounting allowed. Frisch and Smith repeated that comparison in 1963 with a Lorentz factor of about 8.4 and turned it into a teaching film that physics students still watch, and in 1959, Robert Pound and Glenn Rebka measured the gravitational side of the same coin by sending gamma rays up and down a 22.5-meter tower at Harvard, detecting a frequency shift of about 2 parts in 1,000 million. The evidence has been piling up for almost 90 years in different countries with different instruments by people with no particular interest in agreeing with each other, which brings us back to your phone. The satellites of the Global Positioning System orbit at about 20,000 kilometers altitude, moving at around 14,000 kilometers per hour. 2 relativistic effects act on their onboard clocks, and they pull in opposite directions. Because the satellites are higher in Earth's gravitational field, their clocks run fast by about 45 microseconds per day. Because they are moving quickly, their clocks run slow by about 7 microseconds per day. The net is a gain of 38 microseconds every day. 38 microseconds sounds like nothing, but the system works by timing radio signals travelling at the speed of light, and light covers about 300 meters in a microsecond. 38 microseconds of clock error is roughly 11 kilometers of position error, accumulating every single day. If the engineers who designed the system had not built the correction in, satellite navigation would have been useless within 2 hours of switch on and hopeless within a week. The correction is in there. It has been in there since the beginning. Every time a map on a phone knows which side of a street you are standing on, that is a working confirmation of the exact effect that is about to take everything away from our crew. There is more, and it gets more intimate as it goes. The International Space Station orbits low enough that the velocity effect wins over the altitude effect, and its clocks run slow by around 25 microseconds per day. That is about 1/100th of a second per year. When the astronaut Scott Kelly returned from 340 days aboard, the accumulated difference between him and his identical twin brother Mark, who had stayed on Earth, was about 8.5 milliseconds. 2 men, born minutes apart, genetically identical, and now measurably out of step with one another by a specific and calculable amount. The cosmonaut Oleg Kononenko has spent more cumulative time in orbit than any human being, passing 1,000 days on the 5th of June 2024, and finishing with something like 1,111. He has displaced roughly 300ths of a second into the future, relative to everyone he came home to. 3 years of his life, spent at 8 kilometers per second, bought him 30 milliseconds. And at the other end of the scale of delicacy, in 2010, a group at the National Institute of Standards and Technology led by Chin-Wen Cho compared 2 aluminium-ion optical clocks and detected the difference in their rates when one was raised by 33 centimeters, just over a foot. In 2022, a group at Gila resolved the same kind of shift across a single millimeter of a cloud of strontium atoms. We can now measure the difference in the rate of time across the thickness of a coin. So this is not a theory we're about to apply to our journey. It is a description of a universe we have already checked, at every scale we can reach, and it has never once failed. The crew of our ship are not gambling on an idea. They are relying on the same physics that keeps the map on your phone honest. The difference is only one of degree. Their gamma will not be 1.005 or 29 or 70. Theirs will be over 13,000. Let us go and see what that feels like from the inside. The engines light, and for a very long time, nothing interesting happens at all. This is the part of interstellar travel that no film has ever been willing to show you, and it is worth sitting inside for a while because the ordinariness of it is doing something to the crew that they will not notice until it is far too late. The ship leaves the solar system under 1G. Within a few hours it is moving faster than any object humans have ever launched. Within a day it has passed the speed of the Parker Solar Probe. Within a week it is travelling at a substantial fraction of 1% of light speed, and the sun behind it has already begun to shrink toward being a star rather than a neighbour. And still, inside there is nothing to feel. The floor pushes up against the soles of the crew's feet at exactly the rate the Earth used to. Water sits flat in a glass. A pen rolls off a table and lands on the deck. There is no window seat sensation of emotion, because there is nothing to move past. At the end of the first month, the ship is travelling at about 7% of light speed. The Lorentz factor is 1.002. Time aboard and time at home are still, for all practical purposes, the same. At the end of 6 months, the ship is at about 46% of light speed, and gamma has climbed to 1.13. Now the effect is real but modest. For every year the crew lives, the Earth lives about 1 year and 6 weeks, and at the end of the first full year aboard, the ship is travelling at 77.5% of the speed of light. Gamma is 1.58. Here is the number that will unsettle you. In that entire first year, with the engines running continuously, the crew has covered 0.57 light years, not 5, not 50, just over half of 1 light year out of 26,000. If you ran the whole voyage at that rate, it would take 46,000 years. The crew are 1 year into a journey to the centre of the galaxy, and they have not yet made it a seventh of the way to the nearest star. There are some real waypoints in those early weeks, and they are humbling in both directions at once. The heliopause, the boundary where the sun's outflowing wind finally gives way to the gas of interstellar space, sits somewhere around 120 times the Earth-Sun distance. Voyager 1 took 35 years to reach it. Our ship crosses it in about 3 weeks. That is the good news, and it is genuinely good news. In under a month, this vessel does something that took the most successful deep space mission in history the better part of a working lifetime. Then comes the humbling half. Wrapped around the solar system, far beyond the planets, and far beyond the heliopause, is the Oort cloud, the shell of icy bodies from which long-period comets fall inward. Its outer edge is thought to lie somewhere near 1.5 light years from the sun. Our ship, at the end of its first full year, having accelerated continuously at 1G, having reached 77% of the speed of light, has covered 0.57 light years. It is still inside the sun's own cometary cloud, a full year at 1G, and the crew have not yet left the solar system in the larger sense of that phrase. They are still, technically, in the suburbs. This is where a crew's morale would be tested, and it is worth noticing that the test is not physical. Nobody is hurt, nobody is short of anything. The ship is performing perfectly. The problem is purely one of arithmetic and patience, and there is no way to solve it except to keep going and let the curve do its work. It is worth thinking about what the days are actually like, because a video can compress 19 years into a sentence and a crew cannot. There is no port to call at, no waypoint to celebrate, no landmark passing the window. Interstellar space at this stage is not scenery. It is the absence of scenery. The crew's whole world is a few hundred cubic meters of hull, the same faces, the same recycled air, and a view that changes so slowly that you would have to photograph it monthly to prove it was changing at all. Every real long-duration mission we have flown, from Skylab to Mir to the space station overhead tonight, has found that the hardest problems are not the ones in the engineering manuals. They are monotony, confinement, and the slow erosion of the sense that anything you do matters to anyone. Our crew has those problems, and they have them for 19 years and 10 months, and unlike every astronaut who's ever flown, they cannot phone home, because the curve does do its work. That is the strange grace of constant acceleration. Every day the ship adds another 847 meters per second to its speed, and every day that increment matters more, because every day the ship sits a little further up the steep part of the Lorentz curve. By the end of the second year aboard, the ship is at 96.8% of light speed, gamma is very nearly 4, and the distance covered has climbed to 2.9 light years. It has tripled the first year's distance in a single year. By the end of the fifth year, the ship is at 99.994% of light speed, gamma is about 87, and it has covered 83 light years. 5 years in, and the distance is now growing at more than 16 light years per year of crew time. That is the shape of it. Slow, 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 and then everything at once. But while all of that is happening to the numbers, something else is happening to the view, and this is the part I want you to be present for. Imagine you're standing at the forward viewport at the end of the first year. The sky ahead of you is wrong. Not dramatically, not yet, but wrong in a way you cannot stop noticing. The stars have begun to crowd. Where the constellations used to spread evenly across the black, they are now leaning toward the direction of travel, drifting forward as though the whole sky were being gathered in a fist somewhere out beyond the bow. This is aberration. At 77% of light speed, the angles at which light reaches you are no longer the angles at which it left, and the effect is to sweep the universe forward. And the colours have started to move. Directly ahead, the stars are running blue. Not blue like a paint chip, but blue in the sense that everything is shifting up the spectrum toward the shorter wavelengths, so that stars which should be orange are pale and stars which should be white are edged with violet. Behind you, through the aft port, the opposite is happening. The sky astern is reddening and dimming, sliding down toward the infrared, thinning out. The sun is back there somewhere among the fading points, no longer distinguishable, one dull red ember in a sky going quiet. You put your hand on the frame of the viewport and it is exactly as solid as it was on the day you launched. You are, by the ordinary measure of the ship, standing perfectly still. You could set a glass of water on the sill and it would sit there, and out there the entire universe is leaning forward and changing colour. That is the first year. There will be 18 more like it going out, and 19 more coming back, and I want you to understand that the crew will spend almost all of that time doing exactly nothing remarkable. They will eat and sleep and exercise and read and argue and get bored. The ship will hum. The floor will push up at 1G. The stars ahead will get bluer and more crowded and eventually resolve into a single bright disk directly forward, with the whole rest of the sky wrapped around behind it in a narrowing ring of red. Nothing will happen to them. Everything will happen to everyone else. And here is what makes this part genuinely unsettling, once you turn it around. During that unremarkable first year, when the crew was frustrated at having covered barely half a light year, the Earth experienced 1 year and about 4 months. Nothing terrible. A little slippage. Letters home would still make sense. By the end of the 5th year aboard, when gamma is 87, 1 year of crew time is costing the better part of a human lifetime at home. Anyone the crew left behind who was middle-aged at launch is already gone. The institution that funded the mission has been through 4 or 5 complete changes of leadership. The technology that built the ship is obsolete, and the crew are 5 years in, with 14 years and 10 months still to go on the outbound leg alone, and they have covered 83 light years out of 26,000. 0.3% of the distance. The great acceleration has not even started yet. I want to be very precise about what is coming, because it is the hinge of the whole voyage. Everything so far has been the flat part of the curve. Everything from here is the cliff. And there is a single day, about 9 years and 10 months into the journey, when the crew will get out of bed, do some routine work and go back to sleep, and it will cost them more than any other day in human history has ever cost anyone. We are still not ready to answer the question we started with, but we are ready to reach the halfway point. 9 years and 10 months into the voyage, the engines shut down for the first time since launch, and everybody floats. This is the turnaround. The ship has covered 13,000 light years, exactly half the distance, and it is now moving as fast as it will ever move. From this point forward, it has to slow down, or it will pass through the centre of the galaxy at a speed that would render the visit somewhat brief. So the engines cut, the ship rotates 180 degrees on its long axis, and the engines light again, now pointing forward, and begin the 19-year process of bringing all of that speed back off. The manoeuvre takes about a day. It is not difficult. It is the most routine thing imaginable, an attitude change, a burn, a checklist, a confirmation. Let me tell you what that day costs. At the turnaround, the ship's Lorentz factor is 13,418. Its velocity is 0.999999997 times the speed of light. To put that in a form you can hold, if the ship and a beam of light had left Earth together 9 years and 10 months ago, the light would now be ahead of the ship by about 1 part in 300 million of the distance covered. Over 13,000 light years, the light is winning by roughly 400,000 kilometers. That is about the distance to the moon. After 13,000 years of light travel, the ship is 1 moon distance behind the photons. It is worth noticing how quickly that number arrived. At the 5-year mark, the Lorentz factor was about 87. Less than 5 years later, it is 13,418. The final stretch of the outbound half delivers something like 99% of the entire time dilation effect of the voyage. Everything the crew has experienced up to now, all the frustration of covering half a light year in the first year, all the slow grind through the flat part of the curve, was the price of admission to those last few years, where the exchange rate goes almost vertical. Geographically, they are also somewhere real. 13,000 light-years inward from the Sun puts the ship well past the Sagittarius arm and into the inner disk of the galaxy, where the stars begin to crowd together, the gas gets denser and more turbulent, and the whole neighbourhood becomes a rougher place than the quiet suburb we launched from. If they could stop and look around, which they cannot, they would see a sky several times more populated than any night sky on Earth. And with a Lorentz factor of 13,418, 1 day aboard that ship corresponds to 13,418 days on Earth. 13,418 days is 36 years and 8 months. Sit with that. 1 day. Not a decade of travel, not a phase of the mission, not some abstract stretch of the voyage. 1 single ordinary 24-hour period during which the crew wake up, run through a rotation procedure, eat 2 or 3 meals, sleep, and get on with it. And in the course of that 1 day, 36 years and 8 months pass on Earth. A child born on the morning of the launch would, by the end of that single day, be older than the mission itself. Everyone who stood at the launch site and waved has finished their career. The engineers who designed the ship have retired, and the ones who wrote the flight software have died. The parents of the crew are gone, all of them, and the memorial services happened during a period the crew experienced as a Tuesday. Imagine you are aboard for it. You wake up weightless, which has not happened once in 9 years and 10 months, and for a moment you think something has gone wrong. Then you remember what day it is. You pull yourself along the handrail toward the flight deck, and your body, which has had normal weight every single day since Earth, has no idea what to do with itself. Somebody's coffee is floating in a wobbling brown sphere near the ceiling, and there is a small amount of laughter about it. Outside, the sky is no longer a sky. All of the light in the universe has been swept into a hard, bright disk directly ahead, a few degrees across, blue, white, and violent, and behind that disk there is nothing but black. Aberration has folded the entire celestial sphere into a spot you could cover with your thumb. There are no constellations, there is no galaxy, no Milky Way band, no ahead and behind in any sense you grew up with. There is a bright dot, and there is dark. The ship begins to rotate. It takes several minutes. You watch the bright disk slide across the viewport and disappear, and then the black turns slowly past, and then the disk comes back around on the other side, and now it is behind you, and the engines light, and your weight returns, and everything is exactly as it was. The whole thing took a day. While you were floating and laughing at the coffee, your niece was born, grew up, married, had children of her own, watched those children grow up, and died of old age. That is time dilation. Not the formula. That. I said in part 2 that the ship never stops accelerating, and I asked you to hold on to the phrase. Here is what I meant. It is still true. The engines are running, the crew still weighs exactly what they weighed on Earth, and the accelerometers still read 1G. But the direction has reversed. For the entire second half of this voyage the ship is slowing down, and the crew cannot tell. There is no sensation that distinguishes speeding up from slowing down when you are inside the vessel. The floor is the floor, down is down, the coffee still pours. They spend 19 years going out and 19 years coming back, and the experience is identical. And this is not a poetic observation, it is a physical fact about acceleration. The direction of the journey has stopped being something the crew can perceive. It has become a matter of bookkeeping. I would like to make one thing clear before we move on. because people often assume there is a way around this. There is no frame in which the crew is cheating. The crew is not moving through time faster than everyone else, or skipping ahead, or being fast-forwarded. From their point of view, they are stationary, nothing is unusual, and the galaxy is rushing past them, flattened along the direction of motion by exactly the same factor of 13,418. In the ship's frame, the distance to the galactic centre is not 26,000 light-years, it is under 2 light-years. That is why the journey takes them so little time. They are not travelling faster than light, they are travelling through a much shorter galaxy. Both descriptions are correct. That is what relativity means. There is no privileged observer, no true answer, no view from outside in which one of these accounts is really happening, and the other is an illusion. The crew crosses 2 light-years in 19 years. The Earth watches a ship cross 26,000 light-years in 26,000 years. Nobody is wrong, and the two accounts cannot be reconciled into a single story, because there is no single story. There is only what each clock reads. There is an objection that always arrives at this point, and it deserves a proper answer rather than a dismissal, because it has been raised in good faith for 100 years, and it is still raised in bad faith today. The objection goes like this. If all motion is relative and the crew can equally well say that the Earth is the thing moving away from them at nearly light speed, then surely the Earth's clocks should be the slow ones. Surely the situation is symmetrical, and if it is symmetrical, then each side should find the other younger, which is a contradiction, and therefore something in relativity must be broken. The answer is that the situation is not symmetrical, and the thing that breaks the symmetry is the maneuver we have just watched. The crew turned around. The Earth did not. The crew changed which inertial frame they belonged to halfway through, and the Earth stayed in one frame the entire time. Those are physically different histories, and they are different in a way that any accelerometer aboard would record. The cleanest way to think about it is geometric. Every object traces a path through space-time, and the time it experiences is simply the length of that path, measured with the peculiar geometry that relativity supplies. The Earth's path from launch to return is one shape. The ship's path, out and back with a corner in the middle, is a different shape. They start at the same event and end at the same event, and between those 2 points they have different lengths. There is no more paradox in that than there is in 2 roads, between the same pair of towns having different mileages. And this is not an argument to be settled by debate, because it has been settled by measurement. Haffel and Keating's clocks came home from opposite directions, with different readings, and the readings matched prediction. The muons in the CERN storage ring went around a corner 10 to the 18 times harder than our crew ever will, and they lived exactly as long as the asymmetry says they should. The twin paradox is not an open question, it is an experimental result, and here is the piece that I think does the real damage, the piece I want you to take away from this part. Nothing is being taken from the crew. They are not losing time, they lose nothing at all. They get their 19 years and 10 months fully lived at full length, with every day exactly as long as a day has ever been. They are not being cheated. They are, if anything, receiving a gift so large that no one in history has received anything like it. They get the centre of the galaxy for the price of 2 decades. The loss is entirely on the other side. Everything that is being lost by people who never left, who never signed up, who are not aboard, who did not consent, and who will not be told. The crew's bargain is paid for out of somebody else's account, in full, in advance, and the payment is not optional. That day of floating, the coffee, the laughter, the routine rotation, 36 years and 8 months. It was a good day aboard. Now let us go and look at what is happening on the outside of the hull during all of this, because I have been letting you believe that the crossing itself is comfortable, and there is a reason nobody draws the next part on the diagram. Space is empty. That is the first thing anybody ever tells you about it, and it is the reason interstellar travel seems, at least in principle, like a solved problem waiting on an engine. It is also not true, and the degree to which it is not true depends entirely on how fast you are going. The interstellar medium in the general neighbourhood of the Sun contains roughly 1 hydrogen atom per cubic centimetre. 1 atom in a volume about the size of a sugar cube. That is a better vacuum than anything we can produce on Earth. The finest laboratory vacuum chambers ever built still contain thousands of times more particles than that. By every standard we have, interstellar space is nothing. Now put a ship through it at a Lorentz factor of 13,418. In the frame of the ship, Those atoms are not sitting still in a near-perfect vacuum. They are arriving head-on at essentially the speed of light, and each one carries a kinetic energy of about 13,000 times its rest mass energy. For a proton, whose rest energy is 938 million electron volts, that works out to roughly 12.6 tera electron volts. I want to make sure that number lands, because it is the kind of figure that slides past if you're not paying attention. 12.6 tera electron volts is, near enough, the energy of a single proton in one beam of the Large Hadron Collider. The LHC is a 27-kilometre ring buried under the border of France and Switzerland, cool to colder than interstellar space, consuming the electricity of a small city, and its entire purpose is to accelerate protons to about that energy. Our ship encounters them for free, continuously, at a rate of something like 10,000 million per square centimetre per second, across the whole forward surface of the hull, for years. If you would like the total rather than the rate, it is worth doing the sum, because the total is where this stops sounding like a nuisance and starts sounding like a wall. Take a ship with a forward cross-section of about 100 square metres, which is modest, roughly the floor plan of a small house. Fly at 13,000 light-years through gas at 1 atom per cubic centimetre. The amount of hydrogen it sweeps up on the way is about 20 kilograms. 20 kilograms, over half the width of the galaxy. That is the whole harvest. Now convert that 20 kilograms into the energy it carries in the ship's frame, at a Lorentz factor climbing toward 13,000, and you get something in the region of 2.5 times 10 to the 22 joules. Spread across the 20 years the crew experiences, that is an average of roughly 40 terawatts, landing on the front of the ship without pause for 2 decades. Human civilization as a whole currently runs on something like 20 terawatts. The forward hull of this vessel is absorbing about twice the entire power consumption of our species, continuously, from a vacuum, for 20 years. That is not a shielding problem in any ordinary sense. Ordinary radiation shielding works by putting mass between you and the particles and letting the particles deposit their energy in the mass. Particles at LHC beam energy do not stop politely in a few centimetres of aluminium. They punch through, and when they strike a nucleus in the hull, they produce showers of secondary particles that continue onward, and those showers are themselves ionizing and themselves destructive. You do not stop this flux. You dilute it, and you accept the damage, and you replace whatever the damage destroys. And there is worse, because the hydrogen is not the only thing out there. Interstellar space contains dust, real dust, made of silicates and carbon, in grains typically around 1/10 of a micrometer across. A grain that size has a mass of about 1,000th of a millionth of a kilogram. It is nothing. You could not see one. You could not feel 1,000,000 of them land on your palm. At a Lorentz factor of 13,418, one of those grains carries a kinetic energy of roughly 1.2 million joules. That is comparable to the explosive yield of a hand grenade, from a single speck of dust too small to see, and the ship is not going to encounter one of them. And then there is the strangest one, the one that I think is genuinely the most unsettling fact in this entire video, because it takes the emptiest, coldest, gentlest thing in the universe and turns it into a weapon. Filling all of space, in every direction, is the cosmic microwave background. It is the leftover heat of the Big Bang, stretched by 14 billion years of cosmic expansion until it now sits at a temperature of 2.725 Kelvin, a couple of degrees above absolute zero. It is the coldest thing there is. It is so faint and so diffuse that it took until 1965 for anyone to notice it, and when they did, they thought it was pigeon droppings in the antenna. 2 men found it by accident. Arno Penzias and Robert Wilson, working at Bell Labs in 1965, could not get rid of a persistent hiss in their horn antenna. They checked the electronics, they checked the wiring, they evicted a pair of pigeons and cleaned out what they delicately described as a white dielectric material. The hiss stayed. It was the same in every direction, at every hour, in every season, and it turned out to be the oldest light in the universe. They shared the Nobel Prize for it in 1978. You are bathed in it right now. It is doing nothing to you at all. Drive into it at 99.9999999% of the speed of light, and the Doppler shift in the forward direction is roughly twice the Lorentz factor, about 27,000. The characteristic energy of those photons rises by that same factor. What arrives at the front of the ship is no longer microwave radiation. It has been shifted up out of the microwave, up through the infrared, through the visible, and into the ultraviolet, at energies around 18 electron volts, which is above the ionization energy of hydrogen. The effective temperature of the radiation field ahead of the ship is on the order of tens of thousands of Kelvin. The coldest thing in the universe becomes a furnace, and it becomes a furnace purely because you are moving toward it. There is no shielding against this in the way there is no shielding against being inside a star. It is not a beam you can block. It is the ambient condition of the universe, arriving from every forward direction at once, and it is only doing this because of your own speed. Slow down, and it goes back to being harmless. Speed up, and it gets worse. Let me put the three of them together, because that is the environment the hull actually experiences during the middle years of this voyage. A continuous flux of protons at collider energies, a sandblasting of dust grains each carrying the energy of a grenade, and a forward-facing radiation field at tens of thousands of degrees, all of it arriving on the same square meters of the same forward surface for the better part of a decade, and then again, in reverse, on the way home. The proposed answers to this are all speculative, and I want to be honest that none of them has an experimental basis. People have suggested magnetic deflector shields that would sweep charged particles aside before they reach the hull. People have suggested thick ablative ice shields, sacrificial layers of frozen material that are simply allowed to be eroded away. People have suggested sending an unmanned precursor ahead to clear a channel, which does not really work because the medium refills. There is a certain irony in the fact that the most famous proposal for using the interstellar medium, Robert Bussard's 1960 ramjet, tried to scoop the oncoming hydrogen and burn it as fuel. Later analysis showed the drag from the scoop exceeds any thrust you could get from it at these speeds. The Bussard ramjet works beautifully, as a brake, and it gets locally worse as the ship goes in. The sun happens to sit inside an unusually empty pocket of the galaxy called the local bubble, where the density is more like 1/20th of an atom per cubic centimetre, blown clear by ancient supernova. Our route does not stay in the bubble. It heads inward, toward the crowded inner galaxy, where the gas is denser, more turbulent and more magnetized, and where molecular clouds run to hundreds or thousands of atoms per cubic centimetre. The ship's worst conditions are not at the start. They are somewhere in the middle at maximum speed in the thickest gas, with the least ability to do anything about it. There is one small mercy hidden in the geometry, and it is worth naming because it is the only good news in this part. All of this arrives from the forward direction, and essentially only the forward direction. Aberration, the same effect that swept the stars into a disk ahead of the ship, sweeps the hazard there too. The sides and the rear of the vessel are comparatively untouched. A ship built for this journey would not be a sphere or a cylinder. It would be a long, thin needle hiding behind the smallest possible forward face, with everything that matters and everyone who matters stacked in its shadow. So the honest summary of the physical hazards is this. Getting the ship up to speed is an energy problem we have already agreed to handwave. Keeping it intact at that speed is a materials problem nobody has solved and nobody has a credible route to solving, and the human beings inside are by comparison easy. Give them 1G, give them air and food and something to do, and the biology takes care of itself, which is a strange conclusion to arrive at. The people are the least of the difficulties. I have now given you every hazard on this journey except one: radiation, dust, background, duration, isolation. All of it survivable, at least in principle, with enough engineering and enough patience, and none of it is the reason you cannot come back. We have arrived. Let us go and look at what is waiting. The engines shut down for the second time, and this time the ship stays quiet. 19 years and 10 months have passed aboard. The crew launched in their 20s and they are in their 40s now. They have crossed 26,000 light years. They are, at this moment, the first living things from Earth to have travelled more than a few dozen light hours from the star they evolved under, and they are parked at the gravitational centre of the entire Milky Way. Let me tell you what they can see. Directly ahead, at a comfortable standoff distance, there is a disk of absolute nothing about 25 million kilometres across. It is not black in the way a dark object is black. A dark object still reflects a little, still occludes with an edge, still looks like a thing. This does not. It is a region where the sky simply stops. Stars behind it are not dimmed, they are absent, and around the rim they are bent so that the sky appears to peel away from the edge of the hole and wrap around it. The stars that ought to be hidden directly behind it are visible around its edge, twice on both sides, because their light has come around the object on both sides. One detail worth having straight. The dark disk the crew sees is bigger than the event horizon itself. Light passing close to a black hole can be bent onto a circular path, and the region from which no light can escape to a distant viewer is therefore wider than the horizon. The shadow appears about 2.5 times larger across than the horizon underneath it. That is precisely what the Event Horizon Telescope measured in 2022, and it is the reason that image is such a strong confirmation. The shadow's size and shape were predicted in advance from the mass and the distance, with nothing left free to adjust. There is also a strange mercy waiting here, and it runs against every instinct people have about black holes. Tidal force, the difference in gravity between your head and your feet that would tear an object apart, scales inversely with the square of the black hole's mass. A stellar mass black hole would stretch a human being into a thread long before they reached the horizon. Sagittarius, a star, is 4 million times heavier, and its horizon is correspondingly further out, so the tidal stretching there is gentle. A person could, in principle, cross the horizon of this object intact and comfortable, notice nothing in particular as they did it, and continue falling for some minutes afterwards. They could see out. They simply could never send anything back, ever, to anyone. It is the only place in the universe where you can go somewhere and be perfectly fine and be perfectly, permanently unreachable. Around that absence there is a ring of faint warm emission. This is the accretion flow, and it is much dimmer than you would expect. Sagittarius. A star is starving. The gas it captures from the winds of nearby stars mostly gets blown back out before it arrives, and only a trickle ever crosses the horizon. What is left glows in the radio and the infrared, flaring irregularly, brightening by factors of tens over minutes to hours, for reasons that are still argued about. Magnetic reconnection in the inner flow is the leading candidate. Nobody is certain. The crew is watching the flares happen live from close range, which is something no astronomer on Earth has ever been able to do and never will. And then there are the stars. The environment around Sagittarius. A star is not empty. It is one of the most crowded stellar neighborhoods in the known universe. The nuclear star cluster. Tens of millions of stars in a few parsecs, at densities millions of times higher than the neighborhood of the Sun. The sky here is not our sky with a black hole added. It is a completely different sky, dense with light, where thousands of stars outshine anything ever seen from Earth, and the concept of a dark night does not apply. Threading through the innermost part of that cluster is a group of stars that ought not to be there at all. They are called the S stars, and they are the objects Genzel's and Gez's teams tracked for 25 years to prove the black hole existed. The most famous is S2, sometimes called S02. It orbits Sagittarius A star with a period of 16 years and about 3 weeks. On the 19th of May, 2018, it made its closest approach, passing within about 120 times the Earth-Sun distance of the black hole, which is roughly 1,400 Schwarzschild radii. At that moment it was moving at approximately 7,650 kilometers per second. That is 2.5% of the speed of light. A star, an object with a mass many times the Sun's, moving at 2.5% of light speed. During that passage, the gravity collaboration measured something extraordinary. They watched the light of S2 shift toward the red as it climbed back out of the black hole's gravitational well, combined with the transverse Doppler shift from its own speed. The predicted shift was equivalent to about 200 kilometers per second. General relativity says the relevant parameter should be exactly 1. Newtonian gravity says it should be exactly 0. The measurement came back at 0.90 plus or minus 0.09. 2 years later, the same team detected the Schwarzschild precession of S2's orbit. The ellipse does not close. It rotates slowly, exactly the way Mercury's orbit rotates around the Sun, which was the first prediction Einstein ever checked. The same effect that vindicated general relativity in 1915 at the smallest scale in the inner solar system was measured again a century later around an object 4 million times heavier than the Sun. And S2 is not even the fastest. In 2022, Florian Pieska and colleagues reported a star called S47 with an orbital period of about 4 years, reaching something like 8,000 kilometers per second at its closest approach. 4 years. There are people who have owned a car longer than that star takes to orbit a supermassive black hole. The crew are also seeing something no telescope on Earth has ever seen or ever will. From here, the galactic center is simply visible. On Earth it is buried behind roughly 30 magnitudes of dust extinction, which is a factor of about 1 million in visible light. Every image humanity has of this object is radio or infrared, reconstructed, processed, inferred. Nobody has ever looked at Sagittarius A star with their eyes. These 4 or 5 people are the first, and they are seeing it in ordinary visible light, unaided, out of a window. For scale in the other direction, it is worth saying that this is not the largest black hole in the universe, and it is not close. The monsters at the hearts of quasars run to tens of billions of solar masses, hundreds or thousands of times heavier than this one, Sagittarius. A star matters to us not because it is big, but because it is ours, and because it is near enough that a crew leaving Earth could stand in front of it inside a single working life. There is a genuine unsolved problem sitting in front of the crew here, and they are better placed than anyone in history to look at it. Many of the S stars are young, massive blue stars. They should not exist where they are. The tidal fields so close to a 4 million solar mass black hole ought to tear apart any collapsing cloud of gas long before it could contract into a star. This is called the paradox of youth. It was named in the 1990s, and it is still open. The leading explanation is that these stars did not form here at all. A binary pair wandered too close, was pulled apart, one member was captured into a tight orbit, and the other was flung out of the galaxy entirely at enormous speed. Several such escaping hypervelocity stars have in fact been found, running out of the Milky Way and never coming back. There is something quietly appropriate about that, given what tonight is about. The galactic centre makes exiles. Now let me put you at the viewport for this one because it deserves it. Imagine you are floating at the observation blister, the engine's finally silent, and directly ahead of you is a hole in the universe 25 million kilometres wide. It does not look dangerous. That is the first thing that strikes you. It looks calm. There is no maelstrom, no roaring, no visible violence, just a wide circular absence with a soft brownish-orange ring smeared around it, glowing at about the brightness of a distant street lamp. The whole thing sits there, patient, doing nothing. Behind you and around you is a sky like nothing any human eye has seen. Thousands of stars brighter than Venus. The sky is not black. It is a deep glowing indigo lit from every direction at once, and it throws soft shadows across the inside of the hull that shift as the ship rotates. And then something bright comes around the far side of the hole. It is S2 on its 16-year orbit, and even from a safe distance you can see it move. Not over months, over hours. A star visibly moving against the background, curving hard, and as it swings through its closest approach its light reddens perceptibly, dragged down the spectrum by the climb back out of the well. You are watching general relativity happen, at a speed a human being can perceive. You have travelled 26,000 light years, and it took 20 years, and it was, in the end, worth it. Then somebody on the flight deck runs the numbers on the date at home, out of habit, because they run them every week, and nobody says anything for a while. Because here is the thing about this arrival. The object in front of them has not changed in any measurable way during the entire history of the human species. It looks exactly as it looked when the first anatomically modern human opened their eyes, and it will look exactly the same when the sun swells up and swallows the Earth. It is the most permanent address in this galaxy. Back home, 26,004 years have passed, and we are still not ready to answer the question we started with, because there is one more clock at the centre of this galaxy, and it works on a completely different principle. There is a second way to slow down time, and unlike the first one, it does not require going anywhere. Everything we have looked at so far has been about speed. Move fast and your clock runs slow relative to the people you left. That is one half of relativity, the special half published in 1905. The other half arrived 10 years later, and it says something stranger. Gravity does the same thing. Sit deep inside a gravitational field and your clock runs slow compared with a clock further out, and you do not have to move at all. The formula for a non-rotating mass is beautifully simple. Take the Schwarzschild radius, divide it by your distance from the centre, subtract that from 1, and take the square root. That number is the rate at which your clock runs, compared with a clock infinitely far away. Before we go anywhere near a black hole with this, it is worth grounding it in numbers you can stand next to. The surface of the Sun produces a gravitational shift of about 2 parts in a million. The surface of the Earth, compared with a clock infinitely far away, produces about 7 parts in 10,000 million. These are minute effects, but they are not zero, and they are not theoretical. In 1976, NASA flew a hydrogen mesa to an altitude of 10,000 kilometers aboard Gravity Probe A and confirmed the predicted rate change to about 70 parts in a million. And the optical clock results I mentioned earlier are the same effect measured in a room. Raise one clock 33 centimeters above another and it runs measurably faster. Your head is aging faster than your feet, not as a figure of speech, as a laboratory result. The picture also gets richer if the black hole is spinning, and most of them are. Around a rotating black hole, space-time itself is dragged around with the rotation, and there is a region outside the horizon called the ergosphere, where that dragging is so strong that nothing can remain stationary relative to the distant stars. You cannot hover there. You cannot fire your engines hard enough to stand still. You're compelled to rotate with the hole. The innermost stable orbit also moves much closer to the horizon for a rotating black hole, which means deeper orbits are available, which means stronger time dilation is available to anyone willing to go there. Roger Penrose showed in 1969 that you can even extract energy from that region, throwing something in and having part of it come back out with more energy than it went in with, stolen from the rotation of the hole itself. It is the closest thing physics offers to a black hole as a power source, rather than a hazard. Let me walk you down the well. At 10 Schwarzschild radii out from Sagittarius, a star which is about 127 million kilometers, comfortably outside the orbit Earth would have, your clock runs at 0.949 of the distant rate, about 5% slow. You could live there and barely notice. At 3 Schwarzschild radii, which for a non-rotating black hole is the innermost stable circular orbit, the last place you can orbit without falling in, your clock runs at 0.816, 18% slow. Spend 10 years there, and the galaxy outside ages 12. At 2 Schwarzschild radii, 0.707, 29% slow. At 1.01 Schwarzschild radii, hovering just a whisker above the horizon, your clock runs at 0.0995, almost exactly 10 times slow. Spend 1 year there and a decade passes outside. And at the horizon itself the number goes to 0, and the whole question stops meaning anything, because there is no longer any way to compare your clock with anyone else's. Nothing you do can be reported. Nothing outside can reach you and turn around. For a sense of how extreme those numbers are, compare them with the strongest gravitational time dilation available on any solid surface anywhere in the universe. A neutron star of 1.4 solar masses packed into a radius of 12 kilometers gives a factor of about 0.81, 19% slow. If you could stand on the surface of a neutron star, which you cannot, since the gravity would flatten you into a film a few atoms thick, your watch would lose about a fifth of its time relative to the rest of the universe. That is the maximum available anywhere you could physically stand. Our crew, hovering close above the horizon of Sagittarius A star, can do far better than that. Which raises an obvious idea, and it is the idea I want to spend the rest of this part killing. The obvious idea is this: we have a time machine. Use it. Because look what is on offer here. Everywhere else in physics, when you want to change your relationship with time, you have to pay for it. The ship out here had to reach a Lorentz factor of 13,000, which required converting a mountain of matter into energy. Gravitational time dilation costs nothing at all. There is no engine. There is no fuel. You simply move closer, and the closer you get, the more slowly you live, and the whole thing is free. A crew that wanted more time could park in a tight orbit and let the black hole do the work. A crew that wanted vastly more time could hover just above the horizon and take a factor of 10 or 100, or as much as their structural engineering allowed. They would experience a year. The universe would experience a century. And here is why it does not help them, and why it in fact makes their situation strictly worse. Every second they save is charged to Earth. That is the thing about this particular time machine. It only runs in one direction. There is no configuration, no orbit, no depth, no clever maneuver anywhere in general relativity that lets a traveller arrive back earlier than they left, or that slows the clocks of the people they are trying to return to. Gravitational time dilation does not bring the future closer. It pushes it further away. A crew who used the black hole to shorten their subjective wait would emerge to find that the gap between them and their civilization had grown by exactly the amount of time they thought they had saved. They can make their own lives shorter. They cannot make anybody else's longer. This is the point where I should say something honest about the most famous version of this idea. because a very large number of people first encountered gravitational time dilation through a film. In Interstellar, there is a planet orbiting a supermassive black hole, where 1 hour on the surface corresponds to 7 years outside. That is a dilation factor of about 61,000. The physics for the film was supplied by Kip Thorne, who won a share of the 2017 Nobel Prize for the detection of gravitational waves, and who is about as far from a crank as it is possible to be. So the question of whether that scenario is possible has an actual answer, and Thorne has given it. It is possible, and the conditions are severe. To have a stable orbit that deep in the well, the black hole must be spinning at very nearly the maximum rate general relativity allows. Thorne's figure is that the spin must be within about 1 part in 100 trillion of the maximum. He is explicit that this is permitted by the equations and almost certainly never realized by an actual object in nature. Real black holes are spun up by the material they swallow, and the same process that spins them tends to cap the spin well short of the limit. So it is a labelled thought experiment, and I am labelling it. Sagittarius A's spin is not well determined, but nothing about it suggests anything remotely that extreme. The crew are not getting a factor of 61,000. They are getting, at best, a factor of a few, or a few tens, in exchange for parking somewhere structurally terrifying, and it would not matter if they got 1 million. I want to be as clear about this as I can be, because it is the load-bearing point of the whole video. Both of the mechanisms physics offers for changing the rate of time have the same property. Special relativity's version, the one that got them here, moves the traveller forward relative to everyone else. General relativity's version, the one waiting at the destination, moves the traveller forward relative to everyone else. There is no third mechanism. There is no version that moves anyone backward, and there is no version that slows down the world you left. Every tool in the box points the same way, and it is the wrong way for coming home. It is worth pausing on how odd it is that these two effects, which come from completely different halves of relativity, agree so precisely about which direction they point. Special relativity's dilation is about motion through space. General relativity's is about depth in a gravitational field. They were published a decade apart, they are derived from different starting points, and around the International Space Station they actually fight each other, with velocity winning by a small margin. And yet on the question that matters tonight they are in perfect, unhelpful agreement. Whichever one you use and however hard you use it, the traveller ends up further into everyone else's future than they started. There is a coda here that I find quietly enormous, and then we will move on. Sagittarius A star has a temperature. Hawking radiation gives every black hole 1, and for an object this massive the temperature is around 10 to the minus 14 Kelvin. That is 100 trillion times colder than the cosmic microwave background it is sitting in, which means it is not evaporating. It cannot evaporate. It is absorbing far more than it emits, and it will keep absorbing until the universe itself has expanded and cooled below that temperature, which will happen in something like 10 to the 100 years, 10 to the 100, a 1 with 100 zeros after it. That is the lifespan of the thing the crew flew 26,000 light-years to look at. It will outlast the last star, the last galaxy, the last proton if protons decay at all. It is, for every practical purpose, permanent. Now let us go and total up what happened to the other end of the journey during that same period. Let us step back for a moment and put the pieces we have together, because we are far enough in now that the shape is worth seeing whole. We granted ourselves a ship that accelerates at 1g and never stops. We found that it crosses 26,000 light-years in 19 years and 10 months of crew time, and that the same crossing takes 26,004 years at home. We looked at why, and found that the mechanism is measured, confirmed, ordinary physics running in the satellites overhead. We rode out through the slow first year and the vertical climb of the last 4, and we watched one routine day at the turnaround cost 36 years and 8 months. We arrived and found the destination calm, permanent, and strange, and we checked the only other clock physics offers and found it points the same unhelpful way. So the outbound leg is done, and the crew is alive and well. Everything has worked. Now I want to spend this part doing the one thing we have not done yet, which is to take that number, 26,000 years, and refuse to let it stay abstract. Numbers of that size have a way of going soft in the mind. 26,000 years, 52,000 years, 100,000 years, 1,000,000. They all read as the same word, which is lots. So let us not read them. Let us go and stand in them. 26,000 years ago is the departure date, in Earth's frame, for the crew that has just arrived at the galactic center. Here is what Earth was. The planet was sliding into the coldest phase of the last glacial period. The last glacial maximum peaked between roughly 26,500 and 19,000 years ago, so departure sits right at its opening. Ice sheets kilometers thick covered most of northern Europe, Scandinavia, and a large part of North America. Sea level was more than 100 meters lower than it is tonight. Britain was not an island. You could walk from France to England across dry ground, and from Siberia to Alaska, and people did. There was no agriculture. Nobody anywhere on Earth planted a seed with the intention of coming back for it. Farming does not begin for another 14,000 years. There was no writing. Cuneiform, the oldest script we have, appears about 5,300 years ago. So writing is not 1/5 as old as this journey. It is 1/5 of 1/5. There was no wheel, no metal, no city, no state, no money, no arithmetic beyond counting. What there was people. Anatomically and mentally identical to you, with the same brains, the same hands, the same capacity for grief and humour and craft. Somebody, at right about the moment of departure, sat down with a piece of oolitic limestone and carved a small figure of a woman about 11 centimetres tall. It was found in Austria in 1908, and it is called the Venus of Willendorf, and it is roughly contemporary with the launch of our ship. The cave paintings at Chauvet were already ancient history by then, painted some 32 to 36,000 years ago. Lascaux would not be painted for another 9,000 years. Now let me put you there for a moment, because I think it is the only way to feel the number. Imagine you are standing on the Earth of the departure date. It is cold, and it is a particular kind of cold. Dry, windy, continental, the cold of a world with too much water locked up in ice. The landscape is open steppe and tundra grass with stands of pine in the sheltered places. There are horses on the plain, and reindeer, and further off something enormous and shaggy that is not any animal alive today. There is a group of people at a hearth, perhaps 30 of them, and they are doing the ordinary things. Somebody is scraping a hide. Somebody is working a flint core with a punch, striking off blades. A child is being told something and not listening. The fire is the only light for a great distance, and everything anyone in this group knows about the world was told to them out loud, because there is no other way to store anything. Not one of these people can read. Not one of them has ever seen a wheel or a pot or a woven cloth or a domesticated animal or a field. If you told them that the descendants of their descendants would build a machine to cross the galaxy, you would not have the words, and neither would they. That is the world the ship left, and that is only the one-way trip. That is only half of it. If the crew now turns around and comes home, the round trip is 52,008 years in Earth's frame. So run the same exercise again, twice as far back. 52,000 years ago there were still Neanderthals in Europe. They do not disappear until around 40,000 years ago, which means that at the departure point for the round trip there were two kinds of human being on this planet, and neither of them knew the other was the last of anything. Modern humans had reached Australia, somehow across water, which remains one of the more impressive things our species has ever done. They had not yet spread into Europe in numbers. 52,000 years. Let me set that against the only measuring stick that matters here. Human civilization, by any reasonable definition, is about 12,000 years old. From the first farming villages to the first cities, to writing to empires, to telescopes, to the machine you are listening to this on. 12,000 years, start to finish, everything. The round trip is 52,000. You could run the entire history of human civilization, from the first planted seed to right now, 4 times over inside the crew's absence, and still have 4,000 years left at the end for a 5th run to get as far as the pyramids. That is the sentence I would like you to keep. Not the number, the sentence. Everything we have ever done fits into the gap 4 times with room left over, and the crew, meanwhile, is 39.5 years older. They left in their 20s. They come home in their 60s, in reasonable health, with photographs. It is worth noticing what happened to the pace of the loss too, because it was not steady. For the first year of the voyage, the crew and the Earth were nearly in step. 1 year aboard, about 1 year and 4 months at home. Nothing that could not be written off. By year 5, the exchange rate had risen to something like a human lifetime per year, and in the final 2 years before turnaround, the rate goes somewhere the mind refuses to follow, so that the great majority of the 26,000 years is spent by Earth during a stretch the crew experiences as a couple of quiet seasons near the end of a long trip. The loss is not distributed across the voyage. It is concentrated into the part where nothing seemed to be happening. I want to be careful here, because it would be easy to make this sound like a tragedy of separation, a story about people who miss their families. It is not that, or it is not only that. The families are the smallest part of what has gone. What has gone is the category. The crew did not lose their relatives. They lost the existence of a world in which the concept of coming home applies. There is no version of 52,000 years in which you return to a changed society, the way a soldier returns from a long war to a country that has moved on. 52,000 years is not enough time for a society to change. It is enough time for the concept of that society to become archaeology, and then to become geology, and then to become nothing at all, because nothing that far back leaves a record unless it was carved into rock and got lucky. There is a comparison I keep coming back to, and it is the nuclear waste problem. When engineers began designing long-term geological repositories for radioactive material, they were handed a design brief that had never been written before. Construct a warning that will still be understood 10,000 years from now. Not a building that lasts 10,000 years, though that is hard enough. A message. Something that will still say danger to somebody who shares no language, no alphabet, no symbols, and no assumptions with you. Panels of experts worked on it for years. They considered pictograms and hostile architecture, and a proposal to breed cats that change colour near radiation, and a companion proposal to seed folklore about those cats into songs. The honest conclusion of all that work was that it probably cannot be done. 10,000 years is already past the horizon of reliable human communication. 10,000 years is under a fifth of this mission. We know almost nothing about the people at that hearth. We have their tools and a few of their carvings, and if we are fortunate, their teeth. We do not know their language, their names, their gods, or a single thing any of them ever said. That is what 52,000 years does to a record, and that is the amount of time the mission takes. There is a small, sharp detail hiding in that number, which I only noticed while putting this together. Radiocarbon dating, the workhorse method for putting a date on anything organic, runs out at somewhere between 50 and 55,000 years. Beyond that, there is simply not enough carbon-14 left in a sample to measure, and archaeologists have to switch to other techniques entirely. So the round-trip duration of this mission sits almost exactly at the outer limit of the method we use to date human history at all. The crew would be gone for longer than carbon can count, so we have counted it. But counting is not the same as looking, and there are some very specific things waiting at the other end of that gap that I do not think you will have thought of. There is an assumption buried in the word return, and it is so deep in the word that you have probably never had to look at it. The assumption is that the place you left is still there. Every journey any human being has ever made has been able to take that for granted. You go away, the place stays put, you come back, and the difference between the two moments is a matter of degree. The building is older, the people have aged, the shop on the corner has changed hands, but the coordinates hold, and the language holds, and there is somebody at the other end who knows what you're talking about when you say that you have come home. 26,000 years does not preserve that assumption, and it fails in more ways than you would expect. Let me take them one at a time, because each one is a separate small surprise, and together they add up to something. Start with the most literal failure. Earth is not where the ship left it. The Sun orbits the centre of the galaxy at about 230 kilometers per second. That is the actual motion of the solar system, right now, through the disk of the Milky Way. 230 kilometers every second, and it has never stopped. Over 26,000 years, that adds up to roughly 20 light-years of travel. Over the 52,000 years of the round trip, about 40. To be fair to the galaxy, that is not very far in its own terms. One complete circuit of the Milky Way takes the Sun somewhere between 225 and 250 million years, a period sometimes called a galactic year. The dinosaurs appeared roughly 1 galactic year ago. So the 40 light-years the solar system covers during this mission is about 0.02% of a single lap. On the galaxy's clock, the entire round trip is a blink, and the ship and the Earth are both essentially standing still. That is worth holding on to because it tells you something about the mismatch we are dealing with. The journey is nothing to the galaxy. It is everything to the people making it, and to the people who did not. So the coordinates the ship departed from are stale before the crew has finished their first cup of coffee. There is no fixed point to come back to. The solar system has moved on. in the most physically literal sense of that phrase, and if the returning ship aims at where Earth was, it will arrive at an empty patch of space 40 light-years from anything. Now, that is a navigable problem. 40 light-years is small against 26,000, the sun's motion is predictable, and any competent flight plan would account for it. I am not offering it as an obstacle. I am offering it because it is the plainest possible statement of tonight's thesis, written in the geometry of the galaxy itself. The destination has a fixed address. The origin does not. I said in the first part that Sagittarius A star is the address at the centre of the galaxy, and I asked you to write it down. Here is what I wanted you to notice. Of the two ends of this journey, the black hole is the one that stays put. It is the reliable one. It is the one you could give directions to. The home end of the trip is the end that drifts and expires and cannot be relied upon, and it is the end with all the people in it. Next. The sky itself is on a clock, and there is a coincidence here so exact that I checked it 3 times. Earth's axis does not point in a fixed direction. It wobbles slowly, the way a spinning top wobbles as it loses speed, tracing out a circle on the sky. This is called axial precession, and it is why the pole star has not always been the pole star. 4,500 years ago, when the Egyptians were aligning pyramids, the star nearest the celestial pole was Thuban, in Draco. In about 12,000 years it will be Vega. Polaris is a recent arrangement and a temporary one. The period of that wobble is about 25,772 years. The one-way, Earth-frame duration of this journey is 26,004 years. Those two numbers agree to within about 1%, which means that a crew who launched with Polaris overhead and who spent 19 years and 10 months crossing the galaxy would arrive at a moment when the celestial pole had swung all the way around the sky through Vega and Thuban and everything in between, and come back to Polaris. One complete circuit. The sky would look, in that one respect, exactly as they left it. It is a coincidence. There is no physics connecting the wobble of Earth's axis to the distance to the galactic centre. But it is an exact coincidence, and it produces something almost unbearable. The pole star is the only thing about home that would still be right. You can already see a small piece of this drift in ordinary life, if you know where to look. The zodiac signs used in astrology were fixed to the constellations a couple of thousand years ago, and precession has been quietly sliding them apart ever since. When a newspaper says the sun is in Aries, the sun is, as a matter of observational fact, usually somewhere else. 2,000 years of wobble was enough to break the correspondence. Our mission runs for 26 times longer than that, and then comes back. Now the ones that do not come back around. Language does not survive this. No spoken language on Earth can be reliably reconstructed further back than about 10,000 years, and most linguists would say that is generous. Proto-Indo-European, the ancestor of about half the languages spoken today, is dated to roughly 6,000 years ago, and reconstructing it is delicate, contested work. Beyond 10,000 years, the method fails completely, because languages change faster than the signal survives. Whatever the crew speaks, the sounds they make will not be words to anybody at the far end. Not different words, not words. Writing does not help as much as you would hope. The oldest writing is about 5,300 years old, which is a tenth of the round trip, and writing only survives when it is on something durable and gets lucky. Everything currently stored digitally will be unreadable within centuries at the outside, not because the material rots, but because nothing will exist that can read the format. Institutions do not survive it, and this is the one I find most sobering, because we have actually tested it. The longest continuously operating human organizations are measured in centuries, occasionally in a millennium or a little more. Not one thing that human beings have ever organized has run continuously for 5,000 years, let alone 52,000. Every state, every religion, every company, every university, every dynasty, all of them are shorter than the 3rd decimal place of this mission. Even the buildings go. Göbekli Tepe, in what is now Turkey, is the oldest known monumental architecture, put up about 11,500 years ago by people who did not yet farm. It is 1/5 the age of the round trip, and it did not stand as a landmark through those years, waiting to be recognized. It was deliberately buried by the people who used it, and then it was completely forgotten, and nobody knew it was there until 1963. The oldest structure we have is a thing we lost and found again by accident. A few things do come through, and they are worth naming, because they tell you what kind of thing survives. In White Sands, New Mexico, There is a set of human footprints pressed into the mud of an ancient lakeshore, dated to somewhere around 21 to 23,000 years ago. Adults and children, walking, one of them apparently carrying a toddler and setting them down occasionally. That is very nearly contemporary with our departure date, and it survived. So did handprints on cave walls in half a dozen countries, made by people who put a hand against the rock and blew pigment around it. Notice what those things have in common. None of them was built, none of them was maintained, none of them was passed down. They survived by accident, in mud and on stone, precisely because nobody was responsible for keeping them. The things human beings deliberately construct and deliberately look after are the things that go first, because they require somebody to keep looking after them, and nobody does anything for 50,000 years. The constellations themselves deform on this timescale. Every star has its own motion through the galaxy, and over 50,000 years those motions accumulate visibly. The Big Dipper pulls apart. Orion loosens. The patterns that every human culture has used to organize the sky are arrangements of the current moment, and the current moment is short. Even the planet's magnetic field is not a constant. Earth's field reverses on average every few 100,000 years, and it has shorter excursions in between, when the field weakens dramatically and wanders. One of those, the Lachamp excursion, happened about 41,000 years ago, comfortably inside the round-trip window if you count backwards. So here is the full list of what the returning crew can count on. The sun will still be burning. It has 10 billion years of hydrogen, and 50,000 is nothing to it. The continents will be roughly where they were, though the coastlines will have moved with the ice. The pole star will, by coincidence, be correct, and the black hole they visited will be exactly, precisely, unchanged. Everything with a person in it is gone. That is not a failure of the mission. Nothing failed. The ship performed to specification, the crew survived, the science was done, the photographs were taken. It is simply what 52,000 years is. And there is one more consequence of the distance that we have not touched at all yet, which is that for the entire duration of this mission, in both directions, nobody can say a single word to anybody. Light is fast, and we say that so often that we have stopped noticing it is also, for our purposes tonight, unbearably slow. Light crosses 26,000 light-years in 26,000 years. That is not a limitation of our technology. It is the definition of the unit, and it is the absolute maximum speed at which any information of any kind can travel between 2 points in this universe. There is no signal, no carrier, no clever encoding, no entangled shortcut that does better. If the crew wants to tell anybody at home that they arrived safely, the message takes 26,000 years to get there. Now let me lay the timeline out, because the arithmetic produces something I find genuinely lovely, in a bleak sort of way. Launch happens at Earth year 0. The ship arrives at Sagittarius A at Earth year 26,004. At that moment, the crew sends a message home. It travels at the speed of light, and it is received at Earth year 52,004. The ship turns around immediately and starts the return leg, which takes another 26,004 years in Earth's frame, arriving at Earth year 52,008. Look at those last two numbers, 52,004, 52,008. The telegram announcing that the mission succeeded arrives 4 years before the crew does. 4 years, out of 52,000. After a journey to the centre of the galaxy and back, the message and the messengers arrive so nearly together that on any sensible scale they are simultaneous. And the only reason the message wins at all is the couple of years of overhead the ship spends getting up to speed and slowing down again at each end. That is the whole information return of this mission. One transmission, received 4 years before the ship it describes. Think about what that means for the people who launched it. For the entire duration of the mission, and I mean the entire duration, all 52,000 years of it, there is no telemetry. There is no status update. There is no confirmation that the ship survived the first year, or the turnaround, or the arrival. There is no news of a failure either. There is simply nothing, for a period more than 4 times longer than civilization has existed, and then everything at once, and then the ship. Compare that with how we actually operate spacecraft. The signal delay to Mars runs between about 3 and 22 minutes each way, depending on where the 2 planets are, and that delay alone is why rovers have to drive themselves. You cannot steer something in real time when the steering wheel is 11 minutes behind the wheels. New Horizons out in the Kuiper Belt has a delay of over 7 hours each way. Voyager 1 is now more than 24,000 million kilometers out, and the Deep Space Network can still hear it, receiving a signal so faint that its power at the antenna is a tiny fraction of a millionth of a millionth of a millionth of a watt. That is one of the great engineering achievements of the species, and the round-trip conversation time is about 2 days. 2 days, and we consider that a challenging operational constraint. Our crew's round-trip conversation time is 52,000 years. It also runs the other way, and this part is stranger. When the crew arrives at the galactic center and turns their instruments back toward home, the light they collect from the direction of the sun has been traveling for 26,000 years. It left Earth at almost exactly the moment they did. So they arrive at the same instant as their own departure, in a sense. The view of home available to them at the galactic center is a view of the world they left, arriving with them. They cannot see what has happened. They can only see what had already happened when they went, and on the return leg it does not improve in any useful way either. They are flying into the oncoming news at very nearly the speed of the news itself, which means the information about home reaches them essentially only as they arrive. There is no gradual update, no chance to prepare, no long, slow reading in of 50,000 years of history on the way down. The world resolves at the last moment, all at once, at the end of the deceleration burn. It is worth being precise about why there is no way around this, because it is the one place in the video where people reasonably ask whether some future physics might rescue them. Quantum entanglement is usually the first suggestion, and it does not work. Entangled particles produce correlated results, but the results are random at each end, and you cannot impose a chosen message on randomness. Any attempt to extract meaning requires comparing both sets of results, and that comparison has to be sent by ordinary means, at or below light speed. This is not an engineering gap. It is a theorem, and it has a name, the no communication theorem. The other suggestion is some form of shortcut through space-time, and the honest position there is that general relativity permits geometries which would allow it while offering no known way to build or stabilize one. Every wormhole solution written down requires matter with negative energy density in quantities nobody has observed, and most of them collapse the instant anything tries to pass through. It is not forbidden. It is simply not available, and nothing in current physics suggests it is going to become available. So the crew's isolation is not a temporary condition of an early spacefaring civilization. As far as anyone can currently tell, it is permanent, and it applies to anybody, anywhere in the universe who tries this. There is a real precedent for this kind of communication, and it is one of my favourite objects that humans have ever made. In 1974, the Arecibo radio telescope in Puerto Rico transmitted a message. It was a simple thing, 1,679 binary digits, arranged to form a picture if you laid them out correctly. The numbers 1 to 10, the atoms of DNA, a stick figure of a human being, a diagram of the solar system, a sketch of the telescope itself. It was aimed at the globular cluster M13. M13 is about 25,000 light-years away. That is almost exactly the distance to Sagittarius A star. The message will arrive in about 25,000 years, and if anything there were listening and answered immediately, the answer would come back around 50,000 years after transmission. 50,000 years. The same number our mission produces, arrived at from a completely different direction, by people in 1974 who were not thinking about starships at all. They were thinking about whether it is possible to say anything to anyone across that kind of gap. Their conclusion, expressed by the act of sending it anyway, was that you can say something, you just cannot have a conversation. There is a small human detail in the Arecibo story that I have always liked. The message was not really sent to M13. Everyone involved knew that the cluster would have moved by the time the signal got there, and said so at the time. It was sent as a demonstration, to show that we could, and to mark the refurbishment of the telescope. Frank Drake, who wrote it, described it afterwards as a ceremony more than a communication, which is, I think, the correct attitude to take toward any message you send across 25,000 years. You're not writing to a recipient. You're performing an act of faith about the existence of one. The Voyager Golden Record is the other version of the same acknowledgement. 2 gold-plated copper discs carrying greetings in 55 languages, whale song, a Bach partita, thunder, a kiss, a mother and child. Voyager 1 will pass within about 1.5 light-years of a star called Gliese 445 in roughly 40,000 years, and that is the first time it will come near anything at all. 40,000 years. Nobody who worked on that record expected any part of the response to occur inside the lifespan of the species that made it. It was not a message to space, it was a message to deep time, and everyone involved knew it, and they made it beautiful anyway. There is one more asymmetry in here that took me a while to see. On the outbound leg, the crew is flying away from the news, so the world they can observe falls further and further behind. On the return leg, they are flying into it, so the world they can observe races forward at an absurd rate. Tens of thousands of years of history sweeping past their instruments compressed into a couple of decades of their own lives, arriving faster than any human being could read it, all of it already over. If they pointed a telescope homeward on the way back, they would not be watching history. They would be watching a recording on fast forward of a film in which everyone they know appears briefly at the beginning. Which brings us to the thing I have been circling all night. Every one of these examples, the Arecibo transmission, the golden record, the nuclear waste warnings, and our ship, runs into the same wall, and the wall is not physics. The physics is fine. The signal will arrive. The gold disc will still be readable. It is engineered for 1 billion years, and space is a very good archive. The ship will complete its trajectory exactly as computed. Relativity does not fail. Materials do not fail. The trajectory does not fail. What fails is the assumption that there is somebody at the other end. Every one of those projects is addressed to a recipient whose existence is not a physics question, and it is the only part of the problem that none of the equations can touch. So, we have the ship, we have the destination, we have the arithmetic, we have the deep time, and we have the silence. There is nothing left to establish. It is time to answer the question we started with. The deceleration burn ends. 39.5 years have passed aboard. The crew launched in their 20s and they are in their 60s now, and they are, all things considered, in reasonable shape. The 1G held. The bones are fine. The radiation dose was survivable. The ship performed to specification for 4 decades, and it has brought them back to a set of coordinates in the outer solar system, on schedule, with a navigational error of essentially nothing. Imagine you're at the viewport for the last part. The engine's cut, and for the first time in 19 years you are weightless again, and this time nobody laughs about the coffee. Ahead of you there is a yellow star of exactly the expected brightness, at exactly the expected position, having been corrected as planned for 40 light-years of galactic drift. The instruments confirm it. Spectral type, mass, position, proper motion. It is the right star. Around it, the planets are where the ephemeris said they would be, because orbital mechanics does not care how long you have been away. The third one is blue. Somebody at a console begins the standard approach sequence, which includes listening, not for a reply, just listening on every band the ship can receive for anything at all. The sky is very quiet. You keep listening. There is a procedure for this and you follow it, because following it is easier than the alternative. Radio, from the long wavelengths up through the microwave. Optical, looking for anything modulated, anything artificial, anything that repeats. The instruments sweep and log and sweep again. There is a certain amount of hydrogen out there humming at 21 centimeters, the way it does everywhere in the galaxy. There is the soft crackle of the star's own activity. There is the cosmic microwave background, back down at 2.7 Kelvin now that the ship has stopped, harmless again, exactly as cold as it was on the day you left. Nobody says anything for a long time. Then someone asks quietly whether they should try transmitting, and somebody else points out that if there were anything to hear it, they would have picked up something on the way in, and the conversation stops there. The blue planet turns. It has weather. From this distance it looks, in every measurable respect, like the world in the photographs taped inside the crew quarters, which is somehow the hardest part. And that is the answer to the question we started this video with. So let me now state it plainly, because I promised I would, and because you have carried it for 2 hours. What would it actually take to come back from Sagittarius A? It would not take a better engine. The engine was never the problem. We granted ourselves an impossible one in part 2, and the impossible engine turned out to be sufficient. 39.5 years, out and back, 26,000 light-years each way, inside a single working life. It would not take a solution to the radiation, or the dust, or the blue shifted background, or the 12 tera electron volt headwind. Those are real problems, and they are hard problems, but they are the kind of problem that engineering eventually eats. Give it a few centuries, somebody will work out the shielding. It would not take faster-than-light travel or a wormhole or a warp bubble or any of the things people reach for when they want this to be easier. Relativity is not the obstacle. Relativity is the thing that makes it possible at all. Without time dilation, 26,000 light-years would take a crew 26,000 years, and the trip would be flatly impossible for anything with a heartbeat. Time dilation is not the villain of tonight. It is the only reason there is a journey to discuss. What it would take is somebody still being there. That is it. That is the whole answer. The mission requires a receiving civilization, continuous, remembering, still capable of recognizing the ship, still holding the institutional memory that it was sent, across 52,000 years. And that is the one requirement in this entire enterprise that no equation covers, no engineering program can deliver, and no amount of money can buy. Let me put the number against the record one final time, because it is the whole case. 52,000 years. Human civilization from the first farmed field to tonight, 12,000. Writing, 5,300. The longest-lived human institution of any kind, something between 1 and 2,000. The oldest monument we have, 11,500 years, and it was buried and forgotten for most of that time and rediscovered by accident in 1963. Reliable language reconstruction, 10,000. Radiocarbon dating, about 50,000, and then it fails. Every single one of those numbers is smaller than the mission. Most of them are smaller by a factor of 5 or 10. The mission is longer than anything human beings have ever managed to sustain, remember, maintain, or even measure. So when I say that the answer is somebody still being there, I am not being sentimental. I am reporting the result of the comparison. The physics of this journey is solved to several decimal places. The sociology of it has never once been achieved, not by anybody, not for a fifth of the required duration. It is worth asking seriously whether the requirement could be engineered around, because people have tried. One answer is to stop pretending it is a round trip, send the mission one way, with no expectation of return, and the problem evaporates entirely, because a one-way trip asks nothing of the future. This is genuinely the correct solution, and it is the one every serious interstellar study eventually arrives at. It is also an admission. It means the galaxy is open to us for exploration and closed to us for reporting. We could go anywhere. We could never bring anything back. A second answer is to build the receiving institution deliberately, to design an organization whose only job is to still be there in 52,000 years, waiting. Every attempt to think this through founders on the same rock the nuclear waste engineers hit. You cannot write a message that survives 10,000 years. You certainly cannot maintain an intention across 50. Institutions are made of people agreeing to care about something, and no group of people has ever agreed to care about anything for even a tenth of that. A third answer is to change what is aboard. Send machines, which do not age and do not mind, or send crew who are frozen, or stored, or copied into something more durable than a body. This solves the crew's problem elegantly, and it does not touch the actual problem at all, because the actual problem was never aboard the ship. It was always at the other end. And the fourth answer, which is the honest one, is to notice that the requirement is not really about this mission. Every civilization that ever considers doing this will run into it, in any galaxy, at any point in the history of the universe, because it follows from the finite speed of light and nothing else. It is not a limitation of ours. It is a property of the place we live in, and notice where that leaves the crew. They are not lost. This is the part I want to land, and I want to be careful about it, because it is easy to hear this as a story about being stranded in space, and it is not. Nothing failed. The ship did not break down. They did not run out of fuel or drift off course or get hit by a rock. They went exactly where they were pointed. They did the science, they took the photographs, and they came back on time to the right coordinates. By every measure that mission planning uses, this was a total success. They are not stranded in space. They are stranded in time. And the thing that stranded them is not the black hole, and not relativity, and not the 26,000 light years. It is us. It is the fact that the people who sent them could not stay. I said at the beginning of tonight that Sagittarius A star has a fixed address, and I asked you to write it down because I wanted you to notice later which of the two addresses in this story is the one that lasts. Now you know. The black hole is the reliable end of the journey. 4.3 million solar masses, 25 million kilometers across, unchanged through the entire existence of our species, and unchanged for the next 10 to the 100 years. You can give directions to it. You can plan around it. It will be there. The other address, the one with everything you love in it, is the one that expires. And I said something else in part 2, which was that the deal on offer here is 26,000 light years and a career. It sounded at the time like the greatest bargain anyone has ever been offered. One working life, and you get the center of the galaxy. It was an accurate quote. It was just an invoice for something else. The career was never the price. The crew paid a career and they got what they paid for in full, honestly, with no fine print. The price was paid somewhere else, by people who were not consulted, in a currency they did not know they held, and it was paid in advance, and it was not refundable. That is the actual shape of relativistic travel, and I do not think it is discussed nearly enough. Time dilation is always presented as a discount. It is not a discount. It is a transfer. Nothing is saved. The traveller's time is not created out of nothing. It is moved from the account of everyone who stays into the account of the person who goes. The books balance perfectly. They always balance perfectly. That is why it works. There is one more thing I want to say about the crew before we finish, because I have spent 2 hours describing what they lost, and almost none describing what they had. They saw it. That is not nothing. 4 or 5 human beings stood in front of the object at the center of this galaxy and looked at it with their own eyes, out of a window, in visible light, which no astronomer on Earth has ever done or ever will, because 30 magnitudes of dust sit between here and there, and no telescope will ever get around that. They watched a star swing through its closest approach and redden in real time as it climbed back out of the well. They saw a sky with no darkness in it. They spent 19 years crossing a distance that light itself takes 26,000 years to cover, and they arrived healthy, and they were the first. Whatever the invoice said, somebody paid it and somebody went, and the going was real. So here is where that leaves us, and I want to leave you with it gently, because I think it is a thought worth taking to sleep rather than one worth being alarmed by. There are journeys we can take and journeys we can return from, and tonight it turns out those are 2 different lists, and the second one is much shorter than the first. Everything within about 100 light years is on both lists. A crew could go to Sirius, or to the Trappist planets, and come home to a world that had aged a century or 2, which is strange and sad but recognizable. Beyond that, the second list begins to thin out, and somewhere out past a few thousand light years it simply stops. The center of our own galaxy is not on it. Neither is Andromeda, and neither is anything further. Which means the universe is, in a very specific and completely unavoidable sense, a one-way street in almost every direction. Not because we cannot go. We can go in a career to almost anywhere, because there is nothing to come back to. And if that sounds like the end of the thought, it is not, and this is what I would actually like to leave you with. The same arithmetic works in reverse. If anybody, anywhere in this galaxy, ever built a ship like the one we granted ourselves tonight, then the reason we have never met them is not necessarily that they do not exist, or that they cannot travel, or that space is too big. It might simply be that everybody who has ever gone anywhere has been unable to get home to tell anyone about it. There is a fixed address at the center of the galaxy, and there is a soft blue one out here on the edge, and only one of them is still accepting mail. Sleep well.